All right, it looks like we're being live streamed. So, welcome everybody to another meetup this month. Happy to have Sam Dillard, who's our one of our lead product managers at PingCap. Sam, well, happy Monday. Hope you had a good weekend, and I'll let you share the screen and get things started.
Right on. Thanks, Ray.
Yeah.
Pleasure to be here. I'm just making sure that this can be as big as possible. All right, let's go to slideshow. Cool. Is the Zoom stuff in the way, Ray?
No, this is good. So,
Okay, cool. So thanks everyone for joining, and for those who are tuning in later with the recording, thank you as well. I'm Sam, as Ray mentioned. I've been with PingCap for almost a year now. Brought in to do some broad product management across the platform, and so I'm here to deliver some information to you about what is contained in the 7.1 release, which is our latest long-term stable release. So these long-term stable releases will be code supported in full for 3 years and an extra year for critical security vulnerabilities and things like that. So you have 3 to 4 years of support on these releases. So we get a long-term stable, but we'll have many more stable releases between now and 4 years. But if you, for any reason, you cannot upgrade, that's what you're dealing with. So the agenda for the webinar today is pretty simple. I wanted to cover the differences, the key differences between versions 6.5 and 7.1. And the reason I want to do that is 6.5 was the long-term stable release prior to 7.1. So in between there, we had 6.6, 7.0, and 7.1. And I think because most of our customers and even some of our community users only use the long-term stable releases, it's more important to talk about the difference, kind of skip over the non-stable releases and talk about that delta. So that's what I'll do. I'll provide a little bit of some signposting about which version some of these features actually came in if you're interested in that. But the point here is to talk about what's changed in a major way since the last long-term stable or LTS release. The next thing I'll do is talk about 4 key features that came in this delta in a more detailed way. So I'll talk about kind of the problems that we wanted to solve and then how we solved them with those features. And lastly, if there's time, we'll do some Q&A. So the main 3 things I want you to take away from the differences here, I'm gonna lay out a bunch of features, but the 3 major features I think that are going to have large reach and high impact on everybody that uses these things or uses TiDB at all is these 3. So resource control, which is essentially an ability to provide for operators of TiDB to provide resource isolation to their own classified groups of workloads. However they decide to group those workloads or classify them, they can group them into basically resource quotas with resource allotments and a priority that will help for largely increase stability across a cluster, especially if there are multiple workloads running on that same cluster. So this is a huge feature. Nobody really does this today in this space. So this is a big differentiator as well. So I'm really excited about it. I have a blog coming out about it as well in the next few weeks. So stay tuned for that. The second one is distributed online DDL. In 6.5, there was a drastic speed up of online DDL, specifically add index, which is a pretty costly operation. In between 6.5 and 7.1, we released an experimental version of that in a distributed manner, so that drastically sped up that operation as well. And then that will be GA in coming releases, but just know that in 7.1, you have this experimental version of this feature that you can turn on and see how fast you can do add indexes online. And then lastly, multi-rocks, which is actually an internal terminology for something we call partitioned raft key value engine. And so that might be a kind of word vomit right now. So I'm going to hold off, but I'm going to talk about that one in depth later. So all three of these key features are going to be part of that drill down plus one more. But these are the three I want you to kind of remember and bookmark, and I'm going to talk about them in a lot more depth later on in this webinar. So the first, I'm going to group these by category. So between 6.5 and 7.1, the biggest kind of domain, product domain we focused on was performance. And performance includes, in this case, some performance stability as well. So speeding up of operations, but also of making sure that the performance actually remains stable and sort of flat, right? So the first, and anything in green, by the way, is going to be talked about later. So just in case the signposting I've already done wasn't enough, the green stuff is going to be talked about later in depth. So the first thing was this is the multi-rocks thing I was talking about. So this is basically largely to an architectural change at the fundamental level of storage that is not on by default right now because it's experimental as of 6.6, but is a huge change that lends itself to a lot of performance improvements from writes and from scaling in and out. And I'll talk about that. But this is probably the biggest change with the most measurable benefits to our users. And you'll see how that works soon. We added a new lock conflict wake up algorithm, essentially, that in scenarios where you have write heavy workloads that are aimed at the same keys, you may have basically you'll have lock contention, right? And you'll have requests that maybe end up unqueued or waiting for a lock to wake up. And so when the lock is released, there may be several queued requests, and the way that we dequeue those requests was improved dramatically to improve upon tail latencies a lot in write heavy scenarios that especially that have like hotspot keys. So that's a huge one. More to reduce tail latency. We added a feature that we call load-based replica reads. That's GA in this past release 7.1. And what that basically means is that if you have a read-heavy workload where you have hot spotting and on a single node, so a single key range on a node, then the TiDB will quickly, or the storage engine will quickly recognize that situation and offload reads to a replica or a follower, essentially. In a way that maintains snapshot isolation as well. So that will reduce, in those circumstances, that'll reduce tail latency quite a bit. So that'll be a read heavy workload. And that one, so I mentioned 50 to 200%. All three of these performance optimizations fell within that, in the circumstances they apply to, fell within that range. And I think the load-based replica read was the one that increased it by about 100%. So doubled or halved, I guess, the tail latency of these situations. We added an automatic plan cache. I don't know if you're familiar with TiDB necessarily. You probably are to some degree if you're here, but we've had for years a prepared plan cache, which means that with prepared statements, their plans can be cached so that the query optimizer doesn't have to figure out that plan every single time the query comes through, which drastically speeds up performance in a lot of cases. With an automatic plan cache or a general plan cache, the plan cache can apply to non-prepared statements. With some limitations currently, there are certain queries that don't apply, but most queries do apply here. And this cache is at the session level. In future releases, we will have fewer limitations on which queries this will apply to, and we'll make it instance level so that the cache applies to more queries overall. And lastly here is we call batch coprocessor TiKV tasks. So if you're familiar with TiDB, you understand that it's a disaggregated architecture. So TiDB servers will send requests to TiKV servers, which are storage engines, storage nodes. This this feature essentially batches those requests if there are going to be multiple requests to the same TiKV nodes. So essentially, if you have a request to a region of data on a TiKV node and another region of data on a TiKV node and maybe 100 others, all of those, maybe the 102 requests I just alluded to, would be batched into one single gRPC request to the node, which drastically reduces cluster traffic and reduces latency, but increases overall performance of quite a bit. And that was released GA in 6.6. We also increased TiCDC throughput to Kafka by architecturally changing that pipeline. So when TiCDC is collecting data from the storage nodes of TiDB, it will do so in a distributed manner when the downstream is Kafka. In future releases, when the downstream is TiDB, we'll do the same thing, but that's more complicated. So we released the Kafka version first, especially since that's actually the most common use case for TiCDC. And if you're not familiar with TiCDC, it's ping caps or TiDB's change data capture tool. And lastly, in the performance section, we the fast TDL. So I mentioned this already, but we added parallel execution to the add index operation. Parallel execution will apply to more operations going forward, which I'll talk about. On the SQL side, so this category is essentially defined by MySQL compatibility features and just general SQL language features that are kind of you've seen in other SQL databases that are important. So the first thing we GA'd in 6.6 are the foreign keys or foreign key constraints, which basically you're probably familiar with this, but in case you're not, foreign key constraints basically enforce consistency between tables when two tables depend on each other. You cannot write data to a child table if it doesn't have values for the parent table, and so it basically enforces at the database level some business logic that you want to enforce that maybe you don't want to keep track of in your client applications. So this is a huge thing. Also, if maybe foreign keys may not even be important to you, but you may be migrating from MySQL and have foreign keys, and you may get rid of them later, but it just makes migration compatibility more smooth, so that we don't kind of throw up on the foreign key stuff that you have. TTL stands for time to live. This was GA in 7.0. TTL is essentially being able to apply an expiration date or an expiration age, I should say, to the rows of a table. So you define it at the table level and it's enforced at the row level. So essentially it'll expire and then delete rows that have aged out of your window that you define. So you could have a table that's constantly appending new data and you don't want to keep all that data around forever. So you might set a time to live of 30 days or 90 days. And after 30 or 90 days, TiDB will release that data, make it basically available for deletion and then actually delete it. So frees up storage space. It also improves on query performance because it just reduces the number of rows that need to be scanned in a lot of cases, especially in large queries. Larger tables also mean, if you're familiar with the architecture of TiDB, it means more regions or in our case, key ranges in TiKV nodes, which can impact scalability and general cluster performance. So that if possible, it's better to maintain the size of your tables and keep them smaller if you can. It doesn't require there are very, very large tables in TiDB, but when you can manage their size, and TTL helps you do that. And then TTL lastly is also good for compliance, right? If you have regulatory requirements that require data not live for more than a certain amount of time, then you can apply TTL to it and comply with that requirement. Lastly, here is the multi-value index. So MySQL supports this. This is essentially a JSON index, which allows you to store JSON data and then create an expression that creates an index on that JSON data that indexes a JSON array within that JSON blob. So if you're storing a JSON array or a JSON object, you can create an index that basically traverses the JSON tree into a JSON array and indexes the values in that array to the key of the row. So it's an n-to-1 index. So it's similar to the secondary indexes that we already had, but this is an n-to-1 index that allows you to check for the presence of any value inside of an array that's contained in a row. And this is one I forgot to green this one, but that one will be talked about in a little bit more depth later as well.
Hey, Sam,
Yeah.
before we move forward, there's a question that came up online. Is the in-place upgrade possible? Was a question from one of the attendees. Like, I'm not sure if you need more context on this or not, but
Is an in-place upgrade possible? Yes. Yes. By design, an in-place upgrade is possible. It does sometimes depend on the version. If you're going from one version to the immediate next version, it should be easier. If you're going from LTS to LTS, there may be some things you have to change. But it's case by case at the moment. So if that is the case, that will be documented, or you can reach out to us and we can help you through that too.
cool.
In
Thank
most
you.
cases, the in place upgradable. Yeah, but there may be exceptions. And yeah, Ray, this is, I guess, format wise, I'm happy to, let's just do interactive if we want to. That's
Yeah,
probably the
yeah.
way. So
I'll pause things like at logical time spots, I guess, when we have questions. So cool.
cool.
Yeah, and
Sounds good.
thanks for questions, and like yeah, please feel free to post them on Q&A tab, and I'll monitor them as Sam's talking. Yeah.
Yeah, right on. Okay, so from the perspective of stability, scalability, and operability, these are the last three categories. We added resource control. Again, I will talk about that later, so I won't harp on it now, but that's green, and you will learn more about this. My favorite feature of the release. TiFlash is, if you're not familiar, is basically the analytical engine. It's the storage alternative to TiKV. TiKV being the row-oriented storage, TiFlash being the columnar-oriented storage. So if you're doing any kind of full table scans or like you want to do scans that don't require an index, or you're doing any kind of analytical queries against your raw system of record data, TiFlash is a good option for you to add to your storage, and that engine added spill to disk, which essentially adds to stability of large queries against those nodes. That was released generally available in 7.0. So it's generally available now in 7.1. For scalability, this could also be where the multi-rocks or the partitioned raft KB engine, that could go in this category as well, but because it was in the performance, I'll just add that the TiFlash also got a re-architecture. Not quite as significant, but basically it's still significant. We disaggregated the compute and the storage. So TiDB server is already the compute layer, but TiFlash itself has a compute layer within it to do massively parallel processing, MPP. And so we have disaggregated in an experimental way originally, but then we GA'd it just recently to decouple that compute with the storage, so that those can be scaled separately. And then with that change came compatibility with Amazon S3 compatible storage. So you can offload your TiFlash data into S3 to cheapen, in the best sense of the word, the storage of that data. And by separating the compute and storage, a lot of the computing is happening outside of that storage engine. So being S3 doesn't necessarily slow down the operations. Overall, this will reduce the costs of adding in TiFlash, which has been generally the major hindrance between, or getting in the way of people adding TiFlash nodes, because they're like, well, I'm adding a fourth replica of my data. So this will drastically help with that. From an operability standpoint, we added in the load data feature, which actually, this is a compatible syntax with MySQL, but we've actually added a since then, and I feel like I should have updated the slide. I think, or maybe it's in 7.2. I can't remember. You'll have to forgive me on that one. We added import into, which uses the TiDB Lightning import tool as part of TiDB. So basically integrates it into TiDB itself, and then allows it to use all of those features, as well as reach out to remote storage like S3 to grab files of data and import those into TiDB, which really speeds up getting started with TiDB for one, and then also in ongoing imports. If you're offloading data into CSV files and object storage, you can load those into TiDB much more easily now. And then we added a reorganized partition, which is essentially I have a typo there, a syntax sugar for managing partitions. Okay, so I think this is the more fun part. We talk about the details of the really cool features. Ray, is there another? I just saw the comments go up. Is there another question?
No, that was just my comment. So
Okay, cool.
No new questions. Yep.
Okay, I'll rely on you then to let me know.
No worries.
Okay, so the first is the multi-value index. I talked about this a little bit already, but the problems we wanted to solve were that prior to this, users had basically a choice if they had this kind of data. They had to accept very expensive queries where basically they would have to traverse the column that the JSON data was in and walk the JSON data to check for the values in the array in question every time they ran the query, which is basically infeasible. I don't think anyone could successfully do this at scale and have a query return in a reasonable amount of time, if not at all, right? Like sometimes these queries would time out or even crash a node. These are expensive queries without an index. So TiDB wasn't really a good solution for these kinds of use cases where you have to do kind of a quote unquote membership check, which is sort of similar or akin to some full text search capabilities. Obviously, it's not full text search, but a lot of full text search use cases are satisfied with this. The other thing too is if they still wanted to use TiDB and they knew they couldn't use this index, they might have to refactor their schema completely, and probably as well as almost definitely their client application code too, which is just a huge undertaking. So another hindrance of adopting TiDB for use cases like this. The way that we solve this problem is with the multi-value index, which can also be thought of as a JSON index. So what happens here is you have this original table with these three columns: ID, person, and detail, and you write JSON data that includes this key city. In this case, this is the whole JSON blob. And the city is a JSON array of cities. And these cities, let's just say these cities are places that person has ever lived or is currently living, right? And we want to ask of the data, give me which people have ever lived in a certain city, right? So let's say we wanted to ask it which people have ever lived in the city of Albany. So we would create an index that uses an expression like this, which basically traverses the very simple JSON tree to the city key, which returns essentially, the expression would return the array itself. And then we index the array to the key. So we have this multi-value to key index where we see that the key is present in multiple places, but the cities can also be duplicated, right? So we have, if we're searching for Albany, we would walk this index to find these two cases of Albany. And because it's ordered, we know that once we hit Beijing, that's another typo, sorry, then that's all of the Albany occurrences. And so we would then return quickly key 1 and 3. So we know very quickly that Bob and Eddie are the only people who have ever lived in Albany. And we could do the same thing for any of the cities like Oakland and return Alice and Anna. So that is a huge benefit and has enormous performance implications for use cases like this. Okay, onto the big architectural change. This is arguably one of two, if not the most large change that has happened. This is, by the way, not a feature that you are required to use at the moment. It's off by default. It's not technically generally available, even though it is complete. There's various reasons why we haven't made it GA yet, but in the next stable release, it will be GA and probably on by default, but only in fresh clusters. So we don't want you doing in-place upgrades to this new architecture quite yet. Speaking to the in-place upgrades question, this will be more complicated, and we hope to in the future have a better migration path. But right now, it's not. There's a leap, so it's generally better to have to put this new architecture into place on a fresh cluster. That disclaimer aside, I want to talk about the problems that we wanted to solve with this architecture. So the first problem is that in this distributed SQL engine TiDB, we expect to see very large applications, data-intensive applications, and many of them may be in the same cluster. So clusters are expected to be fairly large or hold a lot of data. The more data in the cluster, historically speaking, the more regions, and by regions we mean key ranges. This is an internal term, so it's not like an availability region. This is a region of data, a contiguous data on disk. The more of those regions there are, and the more regions there are, the more heartbeats there are from the raft algorithm within the cluster. And the more heartbeats there are, the closer to topping out the size of your cluster you get to. So basically, there was a theoretical or practical maximum size of a cluster. And so we want to solve that problem. So bookmark that one. The second problem is that there's one single log structured merge tree, LSM tree, for the key value data that you're storing on the TiKV engines. When you have one single LSM tree, for various reasons, you will see quite a bit of write amplification. This is kind of a classic downside of the LSM tree. The LSM tree is a really, really good algorithm, and it's really the de facto one for most NoSQL and even some SQL storage engines like TiDB. But there is this downside of write amplification because due to the way it does compactions. In addition, is it snapshotting the data for backup and restore purposes or for cluster scale and scale out can take quite a while because it's one tree that has to walk and it has to look in, a single set of files for data to snapshot. So bookmark that problem as well. Similar on the having one LSM tree means that all region data is contained in the same files, same set of files. So any reads, writes, or compactions on that data affect all the other regions of the data within that node. So that there's some workload disk IO interference there. And then lastly, I don't think I mentioned this. The current architecture or the historical architecture was that TiKV's core storage engine is RocksDB. There's a single RocksDB that is the backbone of your region data, and it holds all region data at once. And when, in this case, because RocksDB implements for serializability, a global mutex on the write operation, or at basically what we call the apply phase, to make sure that data is being written in a consistent order. And so with that, at the node level, the writes are actually sequential. So there's room for us to speed this up. So the solution was to, hopefully this diagram makes sense, but the solution was to have a RocksDB engine per region of data. So we have many RocksDB engines or instances within the same TiKV node. And that may seem wild to you, but I'll talk about the benefits here. So the first is that we have multiple LSM trees, right? So having multiple LSM trees, going back to the LSM tree problem that I mentioned, there's less data to traverse for one. So snapshotting is a lot faster, and so that'll affect backup and restore speeds. But if you look down here in the bottom right, these are some tests we ran about 5 or 6 months ago. These have been improved since and become more stable since, and we have some large customers in overseas that have been using this in an experimental way and have noticed incredible benefits. The scale out speed and scale in speed were drastically improved. So have at least a 5x improvement on scale out speed and scale in speed on a moderate sized cluster. And I believe the benefit is only greater the larger the cluster you go. So that's huge, right? The whole point of TiDB is to be able to scale and to scale quickly and even auto scale in serverless and with the TiDB operator. So being able to do this quickly is super important. Also, with having multiple LSM trees, there's less interference, workload interference, right? We talked about how the one allows for workload interference, but now that each region has its own files, set of files, then anything that happens, any write, read, or compaction on a region does not affect any of the other regions. It's totally isolated. So that's gonna help with just latencies and general performance. Another thing is that because there's multiple RocksDBs now, remember that global mutex I mentioned that makes writes sequential? Well, now every region can have one of those global mutexes, right? So basically, TiDB as a whole cluster was already multi-write. You could write to multiple regions or multiple nodes at once. But now at the node level, we can write parallel as well. So the write throughput, if you see in this graph, was also increased enormously. So I think up to 300% now is where that is. So it's a pretty big improvement on write throughput with really basically no degradation anywhere else. Also, in having multiple RocksDB instances, we've reduced the write amplification. So there's less compaction of cold data happening because when you kick off a compaction event on region-specific data, it's not compacting all the other regions' data at the same time. So it's isolating compactions as well. And then also we removed the write-ahead log. So that's in less sense, but it's still an impactful one. That this will reduce that sequential I/O as well. The last thing, I'm kind of going in reverse order of the problems I mentioned. This feature, though it hasn't been, this part hasn't been developed yet. If you see this dynamic region size text here, this feature allows for us to make region sizes dynamic in their size, as the name suggests, which means that as regions are cold or hot, so let's say you have a region of data that's a bunch of keys that are less requested, they're written to less, they're read from less, that region is going to be considered cold. And any region that's considered cold can be merged into a larger cold region so that we can reduce the total number of regions, which will reduce the number of heartbeats and then therefore increase the total size of the cluster that we can have. So for many reasons, the cluster size is going to increase a lot. And we expect by the end of this year, at least we hope, to have support well over 1 petabyte of data in a single online cluster. So if you have multiple applications using hundreds of terabytes of data, you could put those all in the same cluster. That's a really big change and fairly unheard of at the moment from online data. So that's the multi-rock solution.
Cool. Sam, a quick question that came up is, are these like the 7.1 features that you're talking about available for open source users only, or is this available for cloud users as well?
Yeah, so that's a great question. Everything I'm talking about here is or is going to be available in the kernel, which is the open source version. And how that applies to cloud is we have 2 cloud offerings. We have a dedicated cloud, which is where most of our cloud customers are today. That is essentially the hosted version of the kernel, the open source version, with some cloud specific features here and there. But the way that works is that will by default the default version will be the latest LTS version, and you can request the non-stable versions if you want, but the default will be the latest LTS version. So today, the dedicated cloud version is this version 7.1. Multi-rocks will be there, but it's off by default, remember? So this, you'd have to specifically, on a fresh dedicated cluster, you'd have to specifically opt into this architecture, but it's also not GA yet, so we wouldn't recommend it. When we recommend it, it will be on by default, and when you start in a dedicated cluster in cloud, you'll have this. The second cloud offering we have is serverless, which is ready to be used, and that has a similar architecture to multi-rocks, but it's actually kind of different. It's sort of a different code base and is more geared towards a serverless the serverless circumstances. So you would have the benefits of multi-rocks essentially inherently, but it would be slightly different architecture. So you wouldn't, by learning this architecture, you wouldn't understand the serverless one any better. but know that those benefits, these benefits really came from concepts that we developed in the serverless cloud.
Cool. Awesome.
Yeah, you bet. Oh, and the last thing here, sorry, is because of the this new architecture, we've also enabled, so we not only enabled the future ability for dynamic region sizing, but we've also enabled the ability to offload storage into S3 too. So each of these RocksDB instances can actually have a different storage device associated with them. So we can have sort of tiered storage in a way which will also drastically improve upon storage costs overall without really hindering performance so much. Okay, two more. So the last one's very short. So another problem solution pattern here. So with a cluster like TiDB, where it's distributed and horizontally scalable, the idea, really the kind of one of the main reasons that you might want to use a distributed SQL engine is to potentially consolidate different workloads, consolidate different applications, or have many different teams or users operating on the same data. Even if that data is online and is actually your system of record or your source of truth. And because it's online and it's a system of record and a source of truth, and you often have critical and strict SLAs associated with the workloads on that cluster, it's very important not to have any interference with those workloads, with those workloads' ability to access data. So problem number one is that foreground traffic, like online data, your online applications that are customer facing, you don't want them to be interfered with by background jobs like adding indexes, DDL, or doing auto analyze, which is the cluster's way of gathering statistics to help the query optimizer, or doing imports or backup and restore, or compactions, right? All of these background jobs can have an effect on the foreground traffic because they're using the same resources. So the problem gets worse too if they're happening at the same time. If a compaction event is going on and then you do an add index and you're not really aware of that, and then an auto analyze gets kicked off or something like that, you can end up stacking up a bunch of background processes that may interfere with your foreground traffic, and the problem gets worse as they stack. So we need to figure out a way to deal with that. Similarly, we need to figure out how foreground traffic themselves, like the parallel foreground traffic, can actually avoid each other. So application 1 and application 2 and user 5 can all operate on the same cluster with basically a guarantee of not interfering with each other's resources, so that the applications can maintain their SLAs and the user can still access whatever's left. And then lastly, even if you solve for workload isolation, how do you prioritize different workloads when there still are resource constraints, right? So we'll talk about all these with the solution of resource control by resource groups. So fundamentally, there's kind of two mechanisms to this resource control solution. One is SQL flow control, which is essentially TiDB server deciding which requests to send to TiKV storage nodes, right? And we'll talk about how it does that in a second. But that's determined by resource groups and the allotment of resources in the resource group. The second thing is actually storage task scheduling. And so the storage task scheduling happens in TiKV nodes directly. And that is also determined by the resource group, but that's determined by the priority set on the resource group. So you can create a resource group and you can set a quota of resources. And the unit of resources is what we call request units per second. Request units are an abstraction of CPU, memory, and disk I/O. Request units per second is a unit of basically how quickly those these units or tokens are backfilled. So it's a matter of kind of how data intensive your workloads are will determine how fast you need to replenish your bucket of request units. So when you set your resource group of request units per second, you say 50,000 or something like that, that's 50,000 request units per second of backfill. So if you use 45,000, then you'll make sure you're kind of always replenished. 45,000 per second. That'd be a very data intensive workload, but by setting it to 50,000, you know that you can kind of always run that workload without really any fear of interference. A resource group can be assigned to any of the following three things: a user on the left-hand side here, a user, a session, or down to the statement level. So a user is going to be, obviously a ad hoc analytical user maybe, but also applications or different workloads, systems like, analytical ETL data pipelines, right? Could be a user that you would assign to a resource group. A session can also be assigned to a resource group. So obviously that assignment will end with the session ending. And then a statement even. So you can provide a hint in a single query that will use a resource group. And you can do that in your application, right? So you can set up, if you have one workload that is designed for resource group one, but in that same workload, there's really this one query that you actually want to run in a different resource group. You can assign that. You can have that hint override its user level resource group and have it use a different resource group. So an application can kind of reach into multiple resource groups if it needs to. And then lastly, you can set a priority on resource group, and that priority can be low, medium, or high. And that priority is what determines how the requests per resource group are scheduled when they're, or basically enqueued in TiKV nodes when they're beginning to stack up. So, if in the cases of having to queue requests and not just being able to serve them right away, priority helps with the order of that queuing. So how it looks in practice, it's as simple as this to create resource groups in the left here. So in this example, we're creating 3 resource groups. One, we have an OLTP resource group, really boring names, sorry, but the OLTP resource group is really our application traffic. This is an online critical application for the business that has strict SLAs. We assign it, I didn't include priority here, we would put a high priority here. We also assign this term burstable, which means that even though we've assigned it a quota of 4,000 RUs per second, if there's resources available and it needs it, it can step outside of its quota and consume more as long as they're available. Similarly, we create a batch resource group, which doesn't require as much. This is probably an analytics pipeline, right? This will be like a Spark workload that'll take some data out of TiDB, munge it, and throw it up somewhere else into a Parquet file or into an analytics system like Domo or Tableau or QuickSight or something like that. Because it's not as critical as the OLTP workload, but if there's data available, these queries can be pretty big. So it'd be nice if we could have it burst as well and have it go outside of its quota when available. Now, since both these workloads are burstable, they're both going to be using whatever's available, right? Which means that they can find themselves in a resource contention situation. So that's where priority comes into play. So having the OLTP workload set to a high priority means that it'll win over the batch, which is what we want. And then lastly, we have an HR workload, which, nothing against HR, but it's going to be it's a deterministic kind of predictable workload. It doesn't have any latency SLAs. So we just need to make sure it finishes, but we don't need it to finish quickly. And we don't expect it to be unpredictable traffic. So we just give it a non-burstable quota of 400 RUs per second, and we call it a day. So the way this plays out is we're going to measure this from two different angles. One is the throughput so basically how much work is getting done by the workload. And then at the same time, the tail latency or the P99 latency of that workload. So in phase 1, we have our critical workload is at its full bore, right? That's high traffic period. So we want it to do as much as it can, as fast as it can. So we see that in green here, notice the legend, green it's running at a high QPS, queries per second. At the same time, we notice that its tail latency is low and flat, which is exactly what we want. Meanwhile, we have the batch workload and the HR workload, which are running at fairly low QPS with some latency spikes, right? So obviously we don't want to see latency spikes with any workload, of course, if we can avoid it. But the point of this is that in these situations where there may be resource constraints and you would otherwise need to scale up your cluster, we're still getting the business logic enforcement that we want, right? We want to make sure that this green line stays low and flat. That's the most important thing, because it's the only thing that has strict SLAs and costs us money if it were to start looking like this. So this is good. In the second phase, OLTP comes down. This is a low traffic period. Maybe it's like overnight or it's weekend or something, who knows? And because of that, some available resources free up. And because the batch workload is burstable, it can spike up to kind of work as fast as it possibly needs to, and its latency will come down, right? And similarly, because resources are still being used, actually, well, the HR workload wouldn't be able to step into that anyways, but the HR workload continues to have a low QPS and somewhat variable latency depending on what's happening in the cluster. In the phase 3, we ratchet back up to the high OLTP throughput, and we notice the pattern repeat itself from phase 1, where the whole time OLTP workloads stayed low latency and flat, so consistently low, which is exactly what we wanted. And then we notice that there's some negative impact on the other workloads. But this green line here is exactly what we want. This means we've achieved our goals. And the last feature that I want to drill into, and this one's the simplest possible one to explain, is the concurrency framework. So with online DDL, that's an expensive operation. There's really no other way to shake it, right? That having online DDL is really nice. It's convenient. It's friendly to users, but it can interrupt things. So we want it to be, obviously we want it to be resource controlled. So that goes back to the feature from before, but we want it to kind of happen as fast as it can and not overload specific nodes. So problem number 1 is that these operations were basically single threaded. A single TiDB node would operate them, and that would be fairly slow compared to alternatives. I mean, to all possible alternatives. Already as an online DDL was faster than really most other solutions, but still wasn't fast enough really to justify kind of mindlessly doing or freely doing add index operations on a live cluster. So the second problem is you could parallelize this on a single TiDB node, but in general, doing the whole operation in one TiDB node is kind of too heavy for the TiDB node sometimes. If you can avoid it, you want to distribute that work and make it more even so that each TiDB node still has a fairly low chance of hitting like an out of memory. So the solution was to distribute the work across TiDB nodes. And so this framework is going to first apply to add index or to DDL operations. But the same framework is actually going to support really all background tasks eventually. So we're going to start having really any background task I mentioned earlier, TTL, time to live, DDL, obviously, backup restore, these kinds of things are going to be conducted in a parallel manner across the cluster. So making them faster and also evenly distributing the work that's done to do these operations. But again, right now it's just add index, but we'd love for you to give this a try and let us know how much faster it really is than what you're used to, or even if you're used to TiDB, how much faster it was than a prior version. Oops, extra slide there. And that's it. Questions from?
Cool. Yeah, one question. I'm looking at both YouTube and Zoom. Do we share like our product roadmap or plans on our webpage somewhere? That's a question.
Yes, we do. Trying to think if we do it for cloud. I believe we do it for cloud. Well, for serverless cloud, I mean, but the serverless cloud is updated every 2 weeks. So the release notes, that's an agile developed offering. I'm not sure it's necessary there, but yes, for the kernel and the open source, which would also apply to dedicated cloud, there is a TiDB roadmap page in the documentation that basically looks out, the next two LTS releases. So it should say, depending on where in the year you're looking at the roadmap, should roughly say, show you what's planned for the kind of key features that we expect to be in the next LTS, and then a little bit looser but still planned the features that we expect to be in the LTS following, which would be 6 months after that. So that roadmap will cover between 7 months and 12 months at a time, basically.
Cool. Yeah, I just pasted a link on both chats on YouTube and Zoom, so hopefully people can check them out. And yeah, like all of our documentation pages, if you have questions, you can open issues, and also you can even directly edit the page if you find anything any changes that you want to request with the pull request.
Yep. So this is the
Cool.
roadmap in case people are wondering. This is actually the I maintain this for the most part. This will be updated in the next week or so. We just released our mid-year LTS release, so we're just waiting to get the final approval from the documentation team. But we will have this, basically this column will shift to the left, and we'll have new stuff put here. So we'll have an end of calendar year LTS release in this column, because that's going to be the next LTS release, right? And then the following one will be a mid-year next year. That's kind of the format of this roadmap, and the roadmap is grouped by those kind of same product domains that I had shown earlier. So this is, if you're interested in reliability, scalability, and performance, then these first two domains will be of interest to you. And then we'll also show you future releases. This one's a lot softer of a commitment. It's really not committed at all, but these are it gives you an idea of which direction we're kind of headed. So you can get a feel for that as well. And of course, we're open to feedback on this stuff, right? That's the benefit of having a community and having an open source product. We can learn from the community if we've missed something, or if we plan to go a direction that's fairly meaningless to the community. We want to know about it, so let us know.
Cool. Yeah, I like the fact that this is part of Docs now. I think it may have been part of like GitHub, like a README file, but I think this is a ride home for it. I think like a final
I
question.
take pride in it too. I think it's not a common thing. I've been in open source for 9 years, and it's my first time managing something public like that. It's I think it speaks to some transparency, which I'm proud to have.
No, that's good. I mean, I think it's best way to solicit feedback too, versus having it in like slides and then you don't know how to get a hold of people with questions. So cool. I think one last question that I'm seeing, I'm assuming this is related to when you talked about multi-rocks and using S3 as a backup storage. The question is, do we support S3 compatible storage for backups?
Yes, for backups. S3 compatible storage is supported for backups, restore, and then those imports, right? As far as having hot data stored in S3, that applies to TiFlash, right? As I mentioned in the re-architecture of TiFlash, if you caught that. And then in the future, because of the multi-rocks, that enables us to soon, that we're in the kind of design phase of this right now, but to soon be able to actually store your hot application data in S3 where applicable, which is very exciting from a billing standpoint, as we probably all know.
Yeah, cool, awesome. Well, thank you, Sam, and just making sure all questions are answered. And thanks for people who join live on Zoom or YouTube live stream, and also for people that will be watching the recording later on. And Sam, we'll plan on having you back with the next stable release by the end of the year. So we'll book you. So.
Glad to hear it. Thanks, Ray.
All right. Thanks.